class. This is again Maria Nanya Rama, your student teacher from Central Mindanao University. And today, we will talk about another topic in Calculus 3. So let's go. Now we have volumes of solids of revolution. Now you are tasked to find volume of a solid of revolution obtained from a simple function y equal to f of x between the given limits x equal to a and x equal to b. Also, you are tasked to find of a solid of revolution using the disk method and the washer method, and we will find out what are those. Okay. So what is solids of revolution? From your previous topic, you have already learned that the area is only one of the many applications of the definite integral, right? Now, solids of revolution are used commonly in engineering and manufacturing. Some examples are axles, funnels, wheels, bottles, and pistons. So, see this video here. I attached the video for your further explanation. Okay? So imagine that the part of the curve between the ordinates x equal to a and x equal to b is rotated about the x-axis through 360 degrees. So imagine that curve, what figure would be resulted, okay? If we have this curve here as y equal to f of x, imagine that it is rotated about the x-axis. Here is our x-axis through 360 degrees. What would be the resulting figure, right? Okay, so the curve would then map out the surface of a solid as it rotated, right? So if that is rotated, if the curve here is rotated around the x-axis, this is the resulting figure. Such solids are called solids of revolution. Thus, if the curve was a circle, we would obtain the surface of a sphere, right? If the curve was a straight line here, if that is a straight line, through the origin, we would obtain the surface of a cone, right? Now, we already know what are the formula of the volumes of the sphere and cone are. So using the form from all those formulas, we will calculate its volumes of the solids of revolution. To see how to carry out these calculations, we look first at the curve together with the solid it maps out when rotated through 360 degrees. So if we take the cross section of the solid parallel to y-axis, this cross section will be a circle. But rather than take a cross section, let us take a thin disk of thickness with the face of the disk nearest the y-axis at a distance from the origin. So now, we have here our radius, y plus delta y, where our delta y here is a change in y because of the small positive increase in x. So here is our y. And here is our delta y. This is the radius of our disk. Now, our height is our delta x. Our delta x is located right from here. This is our delta x. And of course, the volume of solids here of the disk is then given by the volume of a cylinder, pi r squared h, so that we have come out this one. The delta v, or our volume here, pi y squared delta x. Now remember that the formula of a cylinder is pi r squared h. The disk is not a cylinder, right? But it is very close to one. Thus, we will approximate the disk with a cylinder of thickness or height, or our delta x, and our radius y. Now, so the volume of our v of the solid of revolution is given by this one. So if y is given as a function of x, the volume of the solid obtained by rotating the portion of the curve between x equal to a and x equal to b about the x-axis. So we have this one. The volume equal to limit as delta x approaches to 0 of the sum x equal to a to x equal to b delta v. So using the integral, we wouldn't come out a formula which is integral from a to b by y squared dx, or what we call the disk method. Also, we would then use this formula, which is very the same method, pi integral from a to b f of x squared dx, because our y here is equal to our f of x. Now, schematically, this method looks like this. So, from your previous level, I know you have been dealing with it. The volume of disk, we have pi times f of x squared w, where our w here is the width. Then would then come out this representative element, which is the delta v equal to pi of x sub 1 squared delta x. Now, here, the new integration formula for the solid of revolution, we have volume equal to pi integral from a to b f of x squared dx. So the disk method here, a similar formula can be derived when the axis of revolution is vertical or horizontal. Okay, if the horizontal axis of revolution, then we'll have this formula: the pi from integral from a to b f of x squared dx when it is rotated at the x-axis. Now, if it rotated at the y-axis or the vertical axis of revolution, we have this formula: pi integral from c to d g of y squared dy. Now, using the formula, let us derive for the volume of a cone. Suppose that we have a cone of base radius r and vertical height h. We can imagine the cone being formed by rotating a straight line through the origin by an angle of 360 degrees about the x-axis. So we have this resulting figure. So here, what is the coordinate here? So we have 0 and 0. How about this one? Our coordinates here is h and r. Now, using the slope formula, we have y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So our y sub 2 here is our r, and our x sub 2 is our h. And then minus 0, we have r equal to r over h. Now, using the line or point slope formula, we have here y equal to y sub 1 equal to m times x minus x sub 1. So y equal to 0 equal to r over h times x equal to 0. Then we'll have this line y equal to rx over h. It's the limits of integration are from x here, from x equal to 0 and x equal to h. Here is our limit of integration. Here is our 0 and here is our h. And that is rotated about the x-axis. Okay. Then we have, using the formula of the disk or the volume, we have here, substitute the given value, then we have integral from 0 to h pi rx over h squared dx. So substitute the exponent, we have integral from 0 to h pi r squared times x squared over h squared dx. Now, using integration, we have then pi times r squared times x cubed over 3h squared, which is evaluated from 0 to h. Now, we have also a volume equal to pi times r squared times h cubed over 3h squared minus 0, because we will evaluate as the limit of integration. Then we'll have the final answer, volume equal to pi r squared h over 3. Okay, so this is the standard result for the volume of a cone. Now, for activity 1, you can just pause the video and try it on your own. Okay, for the volume of a sphere, we have the equation of x squared plus y squared equal to r squared represents the equation of a circle centered on the origin and with the radius r. So the graph of the function y equal to square root of r squared minus x squared is a semicircle. So now, using the previous formula, derive the equation for the volume of a sphere. Now, you have to first graph the function y equal to square root of r squared minus x squared to see if that is a semicircle. Okay, so you can pause the video and let's check then. So let's check. We rotate this curve between x equal to negative r and x equal to r about the x-axis through 360 degrees to form a sphere. Okay, so here our limit of integration here is negative r and r. So we have here the 2D figure and the 3D figure, okay? So now we have x squared plus y squared equal to r squared, and so we then have y squared equal to r squared minus x squared. Now, therefore, using the formula, we will have integral from negative r to r, or we'll just say negative 1 to 1, pi times r squared minus x squared dx, okay? Then we'll have, using integration and evaluated, then we'll have the final answer 4 pi r cubed over 3, okay? So now, in a sheet of paper, answer this one. You can also answer this one on your own. So this is for the volume of the disk, okay? So using the formula of the disk, you can have the formula to answer this one. So the curve y equal to x squared minus 1 is rotated about the x-axis through 360 degree. Now find the volume of the solid generated when the area contained between the curve and the x-axis is rotated about the x-axis by 360 degree. So try this problem using the formula of the disk, then we will check. Okay, now let's check. To find the points where this happens, we need to set our y as equal to 0, right? So we then map the graph of y equal to x squared minus 1. You can use a Dismos graphing calculator online, or maybe you can graph it on your own. Okay, then we'll have y equal to x squared minus 1, factoring out x squared minus 1 equal to 0. Then we have x minus 1 and x plus 1 equal to 0. Then we'll have x equal to 1 and x equal to negative 1 as our limit of integration, as you can see in the figure. Then we'll calculate the volume as follows. So using the formula of the disk, we have volume equal to pi integral from a to b f of x squared dx. So substitute the given value, we have integral from negative 1 to 1 pi times x squared minus 1 squared dx. Okay, then expand x squared minus 1, we have x to the 4 minus 2x squared plus 1 dx. Now, in using integration, integrate the given value, we have pi times x to the power of 5 over 5 minus 2x cubed over 3 plus x, which is evaluated from negative 1 to 1. So now, we'll have, substituting x, then we'll have these final answer 16 pi over 15. I hope you got it right, class. So the simplest case is when R is the area under a curve y, f of x between x equal to a and x equal to b, which is revolved around the x-axis. So we have here different formulas but the same concept. Okay, we have here pi. First we have here pi integral from a to b f x squared dx, and integral from a to b pi y squared dx and rx squared dx. So that is all the same value. Our f of x could be our y or could be our r of x, depending on you, but the concept is completely the same. Okay, another example, let r be the region under the curve y equal to 2x to the power of 3 halves between x equal to 0 and x equal to 4. Then find the volume of the solid of revolution generated by revolving our r around the x-axis. Okay, so now we'll have, let's set up the disk method for this problem. So using the formula pi integral from a to b f of x squared dx. So substitute the given value here. We can see that in the problem that is between x equal to 0 and x equal to 4. So that would be our limit of integration. So here are 4 and 0. Then substitute the f of x, or the function, given function, we have our y here, our f of x, 2x to the power of 3 halves squared dx. Then perform a simple algebra, then we'll have pi times x to the 4 evaluated from 0 to 4. Then we'll have 256 pi. Okay. Next, another example is the area bounded by the curve y equal to x cubed. the y-axis and the lines y equal to 1 and y equal to 8 is rotated through 360 degrees about the y-axis. So find the volume of the revolution generated. So here is the resulting figure of y equal to x cubed. So we have here a 2D figure and a 3D figure here. So at this point, the axis of revolution is on the y-axis, as you can see, and on the y-axis. So we'll have to use the formula for the y-axis, which is dy respect to y. So here we will note that our y is equal to x cubed. So our x is equal to y 1/3, y to the power of 1/3. So using the formula, we have pi integral from c to d g of y squared dy. So substitute the given value here. We have pi integral from 1 to 8 times y to the power of 1/3 squared dy. Then perform a simple algebra, then integrate from 1 to 8. Then we'll have this final answer, which is 93/5 pi. Okay, I hope you got it right. I hope you are listening. Next, we have the washer method. Okay, the disk method can be extended to cover solids of revolution with holes by replacing the representative disk with the representative washer. So here, our disk is without a hole, but our washer here is with hole. So we can find its radius of the hole and this circle here. Okay. Now suppose the generating region R is bounded by two functions, which is y equal to f of x on the top and y equal to g of x on the bottom. So this time, when you revolve R around an axis, the slices perpendicular to that axis will look like a washers. So a washer is like a disc, but with a center hole cut out. So the formula for the volume of a washer requires both an inner radius and an outer radius. Okay? So here our formula, this is our outer radius here, and our inner radius right beside the hole. Here is our inner radius and our outer radius here. We will find it out. So our formula here will be equal to pi integrated from a to b times f of x squared minus g of x squared dx, where our f of x here is our outer radius and our g of x here is our inner radius. Now, let's have an example. So determine the volume of the solid. Here, the bounding curves for the generating region are outlined in red. The top curve is y equal to x and the bottom curve is y equal to x squared. So here is the resulting figure. So now for the solution, this is definitely a solid of revolution. We'll set up the formula with f of x as x our top and g of x as x squared as our bottom. But what should we use as a and b, or our limit of integration? Now, we'll set f of x equal to g of x and solve to locate these points of intersection. So we have x, our f of x, equal to g of x, or our x squared. So we have x minus x squared equal to 0, or x times 1 equal to x. X times 1 minus x equal to 0. So we find two such points, which is x equal to 0 and x equal to 1. So let us set our a as our 0 and b our 1 in the formula. So now using the formula here, let's find out. Okay, our f of x is x, and g of x is x squared. Okay, that is both squared. So perform a simple algebra here. So we have x squared minus x to the fourth, then evaluated from 0 to 1, integrate. So we have x squared would be x cubed over 3 minus x to the fifth over 5. Then we'll have the final answer 2 pi over 15. So next, another example, last example for this video. So let R be the region bounded in the first quadrant by the curve y equal to 1 minus square root of x the x-axis and the y-axis. Determine the volume of the solid generated when R is revolved about the line x equal to negative 1/4. So here is it is rotated about the y-axis, and here is our resulting figure. So we'll our 1/4 negative 1/4 here is this one, and our outer radius is the curve plus our radius, outer radius, which is negative 1/4. Okay, then for the solution, we will then y equal to 1 minus square root of x, then we'll equate x. So we have x equal to 1 minus y squared. So using the formula, let us input the given values here. We have pi integral from 0 to 1 times 1 minus y squared plus 1/4 squared minus 1/4 squared dy. Okay? If you are wondering that how come na bakit ito naging positive, then so given value is negative. It is because we are talking here the distance. Okay, we are talking here the distance of our radius or a measurement. So wala namang measurement or distance na negative, so lahat ay positive. So we'll give as 1/4 as positive here. So using the algebra, then we have 1 minus y squared plus 1/4 squared minus 1 over 16 squared. Then expand, then integrate using evaluated from 0 to 1. Then we'll have the final answer, which is 11 over 30 pi. Okay, so that's all for today, class. Thanks for watching. Thank you for listening, and see you on my next one. Bye!